here's the test. Okay, and you see from the test, it's completely problem oriented. There's no questions on this one. All right, it's going to have 3, just like this has, problems on just solving for the concentrations or dilutions. Then it's got 1 or 2 solubility product ones where you're solving for KSP, 1 or 2 where you're solving for X, and then 2 where you're doing a precipitate. And then the last one is the one you have to do on your own. The other one's not represented up here. Everything else, every one of those is on this sheet. It's up here too. I mean, it's really very easy. There's no surprises. The only one it's not, of course, is the one you were doing on your own, and that's basically where you had to solve for one of those ions. You know, like that. What really wasn't very hard. It was like a page and a half of actual, notes to take on that. Maybe 1 example or 2. All right, so let's go over these first and try to point out your mistake.
What page exactly?
Yeah, well, you'll have to do that on your own. Let's see what page it was. Probably right there. Okay, I'll put that back up on the in a little bit. They did that day before yesterday or yesterday? Because you guys had the lab the day before that. Right?
We don't have both on the same day.
Oh, that's right. Because the lab didn't take the whole. That's right. The lab didn't take the whole period. I thought it did. It was the Chem 1 lab that took the whole period. All right, let's do this guy here. All right. If you want, I mean, it's very easy to make a dumb mistake along any of these. And so if you want to make sure you don't lose all your points, make sure you show me the work, which includes writing the equation. Moles of solute per liter is the solution. All right. Showing me the formula, showing me the work, 20 grams of NaCl. Convert it from grams to moles. 1 mole contains 58.443. You get that by adding up Na and Cl. Probably get something bigger than that on the test. 2,000 milliliters is 2.000 liters. Do the math for that. What do you get? 171 molar. That's it. Okay. There'll be one that easy on the test, I'm sure. All right. There'll also be one working at strawberries and baskets kind of problem, where you've got. And they say, well, that doesn't really look like that, because you have to understand what molar means. 0.240 molar means 0.240 moles per liter. You have 0.5 liters. That's why I call it a strawberries and baskets problem. If you have 2 pounds per basket and you pick 4 baskets, so all you do is multiply. You can also look at it as a conversion factor. Very simple. Just follow the units. That'll leave you with moles. And a question may ask you for moles. This one asks you for grams. You have to go 1 step beyond that. You have your moles now. You put moles in the bottom, grams in the top. 1 mole contains, for chlorine gas, it is diatomic 70.906. Some people always say, well, I thought you said there aren't any diatomics when we're doing these. That's, first of all, never said that. All right. If I have salt breaking up into water solution, you're right. I get sodium ions and chloride ions. All right. You don't get chlorine gas. This is not what's happening here. This is dissolving chlorine gas. So chlorine is a diatomic element. You have to remember that. All right, so it depends on what the question's asking you, what you're supposed to be doing. All right, so when you're doing a solution later on in a few minutes, I'm going to be writing these. I'm not going to write chlorine gas. All right, because that's different. All right, last one is a dilution one. All right, if you look at the dilution one, you know what to do on these. M1V1, M2V2. All right, your initial concentration is 14.0 molar. And it wants to know how many milliliters of that stuff you need, so that's your unknown. Your M2, what are you trying to get? You're trying to make 0.900 molar. You had a lab where you had to do this kind of stuff. And your V2, how much of it you need is 1.40 liters. This is a very practical question, the kind of question you would have to answer for yourself in a lab in college when making up your own solutions. Many times you'll be told you need this much of this concentration from this stock bottle. You got to do a dilution. All right. In this case, M1V1 equals M2V2. Your V1 is what you're looking for. You'll divide both sides by M1. And V1 equals M2V2 over M1, or you plug it in. I'm not going to do it. You plug all those numbers in, obviously, to show me the full work. What do you get for the answer?
At 90 milliliters.
90? Okay, 90.0 milliliters. That means you'll need that. That's the answer to the question, but I could have asked it, and I have asked some of the other ones in different ways. I could have asked how much water do you need? And you'd have to subtract the 90 from 1.40 liters. You do not need 1.40 liters of water. But I didn't ask that in this question. That's all you would have to put, 90 milliliters. Okay. You had to worry about that kind of stuff when doing the lab back there yesterday or the day before. Okay. So those are the easy ones. Those are the ones you could have done in Chem 1. They really are that simple. Now, let's talk about the KSP ones, which you could not have done in Chem 1. You didn't know about equilibrium. You certainly didn't know about KSP. Well, turns out that these are of the 3 chapters on equilibrium. You have to admit this is the easiest one. All right? You do not have a denominator. You don't even have to worry about the simplifying assumption. You certainly aren't going back to those calculators and using the quadratic formulas. None of that stuff on here. It's pretty simple. All you have to do is write the equation down. In this case, oops, it's the dissolving of K2SO4 in water. So K ions and SO4 ions. Okay, if you want to get full credit, you got to remember these charges, aqueous and balanced. Right? And you're told the concentration. Well, actually, in this case, you're not told the concentration. Some of them, maybe one of them on the test, you will be. Maybe one of them will give you grams. This one that does it, you have to do the molarity again. Show me the formula, show me the work, moles per liter, 0.0435 grams, converted to moles, over 2.0 liters. When you do all that, what do you get for the molarity just? 2 point what?
0.028.
Oh, 0.02.
1.8.
All right, so that would be 0.0218 here. 0.2 times 0.0218. This number doesn't seem familiar from last class. Sure, that's right. Everybody else
I
get
got
that?
0.0001.
I was going to say, I didn't sound familiar. Yeah, that didn't sound familiar from the last class. What do we do wrong here? You should have taken 0.0435, and what was the molar mass of the K2SO4? 174 point something.
Yeah, I did change it to moles.
There you go. All right.
Divide by 2, right?
And then you have to divide by the liters solution. Okay, 2. Okay, so that should give you, what was the number again? The real. I didn't think that sounded familiar from last period. So it's what up here?
0.00012.
0.00012. Should be one more significant. No, it shouldn't. That's 2.0. Right. But 0.00012 is correct. All right. Everybody else get that? Right?
Yeah.
All right. That's 2 times that number, and then 0.00012. All right. Now I have to do. Remember, at this point, I'm hoping no one's going to solve for KSP when they're supposed to be solving for X, or solve for X when they're supposed to be solving for KSP. This one wants you to get KSP. This is not X here. You don't put X, 2X, and X. That's not what you're doing. All right? You're trying to solve for KSP. KSP equals, show me the formula, K times SO4. Right? It's not even a denominator. So it equals...
Is K squared?
Oh, yeah, K squared. Because you have to put the raise to the coefficients. But there's not even a denominator. So now we plug our numbers in. So it equals 0.00024 squared times 0.00012 molar. That's molar 2. So what do I get?
6.9 times 10 to the negative 12.
Anybody else get that? 6.9 times 10 to the negative 12 molar cubed, correct? Right? Because you have molar squared and times molar is molar cubed. All right, and there's KSP. So, what are the mistakes you can make? Well, you can make, if you show me the work and you made a mistake in here, I mean, you're going to lose some points. What Liz did would be wrong, and not just 1 point off wrong. She divided grams by liters. That's not molarity, all right? But a smaller mistake would be just putting the wrong molar mass down. You know, you added up K2SO4 incorrectly. That would be a smaller mistake. An even smaller mistake would having everything up here right and just doing the calculator wrong. It'd be 1 point off. All right, but that's why you show the work for all this. Otherwise, you're going to lose a lot more points. All right, let's look at number 5. This guy wants you to work backwards. Wants you to get X. All right, because it gives you KSP. So I'll write the equation again, like you always do. Zinc hydroxide. I have to write zinc hydroxide. Why you need a common ion sheet, those of you who just got one. You need zinc hydroxide written correctly. -1 + 2 zinc OH2 dissolving in water into zinc ions, aqueous, and hydroxide ions. 2 of them aqueous. Okay? You know KSP. So you have basically X and 2X. Right? That's what we care about. And this is X also. Alright, so KSP equals zinc's concentration times hydroxide's concentration squared. So basically it's X, this is 4.5 times 10 to the negative 17th, X times 2X quantity squared. Now that means you don't have, a lot of people will do this, 2x cubed. It's not. It's 4x cubed. You see why? Right? And then equals 4.5 times 10 to the negative 17th. Do the divide by 4, take the cube root. What do you get?
2.2 times 10 to the negative 6.
Everybody else get that? Negative 6? Okay. That is your molar solubility. That's the answer to this one right there, because that happens to be what X is right there. So it is the molar solubility. All I got to do with that number to get the gram solubility, moles in the bottom, grams in the top. 1 mole contains, for zinc hydroxide, it's like 99 or something like that. And what do you get for your gram solubility?
2.2 times 10 to the negative 4.
Right? Makes sense? All right, so that's pretty easy. So here you're solving for X. Last one you were given X, you're solving for KSP. And this last one, which is probably the one you have the most chances to get something wrong on, because you have to dilute the stuff, you got to look up the right guy in the back, although I'm going to give you the KSPs. All right, you got to cross them, you know, like which ones are mixing with who. And then you got to actually do the calculation. This one's probably the most likely to see a mistake on, a dumb mistake, like you saw in the lab. You guys all knew you were supposed to take the dilutions, but some people didn't. All right, so let's do this guy. I'm going to write the equation for sodium sulfate breaking up. First, he becomes sodium ions, aqueous, and sulfate ions, aqueous, 2 of them here. I know I have 0.001 molar added to 100 milliliters of something else. So it becomes 0.00050 molar, 2 times 0.00050, and 0.00050 molar. Okay? That's how they break up. The other guy breaks up, barium chloride breaks up into, again, here's one where you don't get chlorine gas. Nowhere do you do that when it's just dissolving in water. Barium ions and chloride ions. I need 2 of them, 2 chloride ions. And I start out with not 0.01, but rather 0.0050. And if I give you a harder one to do, you just have to do the dilution factor, which, by the way, I showed you a short way to do that, right? All you got to do is take the concentration you have and multiply it by the volume you have, divide it by the total new volume. That's all you really have to do. You don't have to show me all the M1, V1, M2, V2, except in the problem where I ask you to do that. All right? Molar, 0.00500 more, and 2 times 0.00500 more. Good. Now, here's the interesting part. You got to remember, when you add these 2 guys together, we're assuming they were clear solutions and they both dissolve. Now, I'm going to see if their new guys that you formed over there happen to give you a precipitate. Sodium chloride, I look up in the back. I'm not going to find anything for him. You know that. He is soluble. The barium sulfate, I do. What is the KSP for barium sulfate, by the way?
1.1 times 10 to the negative 7.
All right, so I'm going to compare my answer to that. All right, I want to see what my answer comes out to be. So let's solve for Q. QSP is basically KSP, just calculated somewhere else. We don't know if it's at equilibrium or not. So, by the way, for QSP, I better write the equation for barium sulfate. This is the guy I'm crossing. Barium sulfate is breaking up into barium ions and sulfate ions. Why do I have to write this out, even though I might have KSP written for me? To see, and it doesn't happen in this case, but to see if I'm going to have a 2 here or a 3 there or something like that. Because that will change my QSP calculation. Barium times sulfate, right? In this case, there are no other coefficients, so I don't have to worry about it. Now I just plug my numbers in. The numbers I get from here and there. Okay, I get from this guy. So they're 0.00500 more times 0.0000500 more. And what do I get for my QSP?
2.50 times 10 to the negative 6.
And that is larger than that, which means there is a what? Precipitate. Now let me just say something before you leave this one alone. All right, kind of important here. Listen to this. I didn't do one here with it, but I know I did one in your notes like this. Say this barium sulfate broke up. It was like Ba3S2. Say that's what the actual formula was. And you had to have 3 here and a 2 there, right? If that was the case, your equation would become Ba, cubed and this guy squared. But what you don't do is multiply by 3 this number or that number, right? Because they came from a different source, okay? That's kind of important. All right, no surprises. The only thing left to do on your own is that 1/7.